So, what's up everyone? It's FYI here. Ever wondered what makes your smartphone tick? I mean, we use these things every single day, they're basically an extension of our hands at this point. But what's actually happening inside this sleek slab of glass and metal that lets you scroll through social media, game, and connect with people across the world? It all comes down to one incredibly complex, beautifully engineered component, the motherboard. Today we're diving deep into the world of smartphone motherboards. We're going to take a look at what they are, what every little chip does, and how it all comes together. This isn't going to be some super technical, jargon-filled lecture. The goal here is to break down this intricate piece of technology in a way that anyone can understand. We'll go piece by piece, component by component, from the bare board to the final, fully assembled brain of your phone. Think of it like building a Lego set, but on a microscopic scale with way more electricity involved. It's a fascinating process, and by the end of this, you'll have a much deeper appreciation for the engineering marvel you carry in your pocket every day. We're going to cover everything from the main processor, the memory, the power management, all the way to the tiny connectors and sensors. We'll look at how your phone connects to Wi-Fi, how it knows which way is up, and how it manages to power everything without, exploding. It's the central nervous system, the circulatory system, and the skeleton of your device all rolled into one. Ready? Let's get into it. Alright, so first things first. Before you can have a motherboard, you need the board itself, and that is the printed circuit board, or PCB. This is the foundation, the literal bedrock on which everything else is built. If you've ever seen the inside of any electronic device, you've seen one of these. It's that green or sometimes blue or black flat board that looks like a miniature city map with tiny roads and buildings. It's our starting point for building the brain of the smartphone. The primary job of the PCB is to provide a physical structure for all the components to be mounted on. But more importantly, it's about connection. Those roads you see are actually tiny copper pathways called traces. These traces are etched into the board and they're what allow electricity and data to flow between all the different chips, resistors, and capacitors. Without the PCB, you just have a pile of disconnected components. It's the superhighway system that makes communication between every part of the phone possible, all in a super compact space. Now, smartphone PCBs are a special kind of impressive. Because space is at an absolute premium inside a phone, these aren't just single-layer boards, they are multi-layered. Imagine taking 10 or 12 of those city maps and stacking them on top of each other, with tiny vertical tunnels called vias connecting the different layers. This allows engineers to create an incredibly dense and complex web of connections in a very small footprint. It's a level of miniaturization that is honestly mind-boggling when you stop to think about it. So you start with this blank, multi-layered board. It's a clean slate. The design has been meticulously planned out by engineers using sophisticated CAD software to ensure every one of the thousands of connections is perfectly routed. They have to consider signal integrity, power delivery, heat dissipation, and 100 other factors. The placement of every single component is deliberate, and it all starts with the layout of these copper traces on and inside the PCB. It's the unsung hero, really. Without a well-designed and manufactured PCB, nothing else matters. The fastest chip in the world is useless if it can't talk to the memory or get clean power. So as we begin to populate this board, remember that this carefully constructed foundation is what makes all the high-tech magic possible. It's the canvas upon which the masterpiece is painted. Next up, we'll place the most important component, the brain. Okay, so we have our foundation, the PCB. Now it's time to install the brain of the entire operation. This is the system on a chip, or SoC. You've probably heard this term thrown around a lot in phone reviews. Snapdragon, A-series Bionic, Tensor, Dimensity. These are all SoCs. And it's called a system on a chip for a very literal reason. It's an entire computer system integrated onto a single tiny piece of silicon. This is the single most important and usually most expensive component on the entire motherboard. At the heart of the SoC is the CPU, the central processing unit. This is the primary thinker. It's responsible for running the operating system, your Android or iOS, and executing the commands from all your apps. When you tap an icon to open an app, the CPU is what processes that request and gets things moving. It's composed of multiple cores, some high performance for demanding tasks like gaming, and some high efficiency for background tasks to save battery life. It's the core of the user experience. But the SoC is so much more than just a CPU. Integrated right alongside it is the GPU, or Graphics Processing Unit. The GPU's job is to handle everything you see on the screen. It renders the user interface, decodes videos, and most importantly, powers your games. A powerful GPU is the difference between a smooth, high frame rate gaming experience and a choppy, laggy mess. The CPU and GPU work in tandem, but they are specialized for their different roles. And it doesn't stop there. The SoC also contains a whole host of other critical processors. There's the ISP or image signal processor, which takes the raw data from the camera sensor and turns it into the beautiful photos and videos you capture. There's a DSP, digital signal processor, for handling complex mathematical tasks efficiently, like analyzing audio. Many modern SoCs also have a dedicated NPU, or neural processing unit, specifically designed to accelerate AI and machine learning tasks, like real-time language translation or computational photography. So when we place this one chip onto the motherboard, we're not just adding a processor, we're adding the central hub for processing, graphics, imaging, AI, and so much more. It's an incredible feat of integration. All of these different, highly specialized units living on one chip, communicating with each other at incredible speeds. The performance of your entire phone, how fast it feels, how good the photos look, how long the battery lasts, is largely dictated by the capabilities of this single component. With the brain, the SoC in place, it needs two other critical things to function: a workspace and a filing cabinet. This is where memory and storage come in, and it's super important to understand the difference between the two. They work together, but they serve very different purposes. Let's start with the workspace, which is the RAM, or random access memory. You can think of RAM as the SoC's short-term memory or its desk. When you open an app, the phone pulls the necessary data from the slower, long-term storage and loads it into the super-fast RAM. The SoC can then access this data almost instantly. The more RAM you have, the bigger your desk is, and the more apps and processes you can have open and ready to go at the same time without the phone slowing down. When you switch between apps and it's instantaneous, that's because the app was sitting in RAM, waiting for you. This is why having more RAM, 8, 12, even 16 gigabytes, is key for heavy multitasking. Now, RAM is volatile memory. That means when the power is turned off, everything in it disappears. Your desk gets cleared overnight. So you need a place to permanently keep your files, your apps, your photos, and the operating system itself. That's the filing cabinet, the internal storage. This is non-volatile memory, usually in the form of a NAND flash chip. When you see a phone advertised with 128, 256, or 512 gigabytes of storage, this is what they're talking about. The type and speed of this storage matter too. Modern phones use standards like UFS, Universal Flash Storage, and the faster the storage, the quicker your apps will load initially, the faster files will save, and the quicker the phone will boot up. So, while RAM affects how many things you can do at once, storage speed affects how quickly you can start doing those things. Both are soldered directly onto the motherboard, usually very close to the SoC to minimize the distance data has to travel. So, to recap the relationship, when you turn on your phone, the operating system is loaded from the permanent storage filing cabinet into the temporary RAM workspace. When you tap on an app, it too is loaded from storage into RAM. The SoC does all its work with the data in RAM. When you save a photo, it's written from RAM back to the permanent storage. Having a good balance of fast RAM and fast storage is absolutely crucial for a phone that feels quick and responsive in day-to-day use. Okay, so we've got the brain, the workspace, and even the filing cabinet, but honestly, none of it works without electricity. And you can't just connect a battery directly to the SoC and call it a day. That would be like hooking up a fire hose to a drinking fountain. Definitely not a good idea. Different components on the motherboard need very specific, stable voltages to operate correctly, and that's where the Power Management Integrated Circuit, or PMIC, really comes in. This is kind of the unsung hero of battery life and stability. The PMIC is basically a highly sophisticated power distribution hub. It takes the single voltage coming from the battery, let's say it's around 3.8 volts, and it uses a series of regulators and converters to create all the different voltages needed by every other part of the phone. The SoC might need multiple different voltages for its various cores, the display needs its own specific power rail, the cameras need another, the RAM needs another, and so on. The PMIC manages all of this at the same time. It's honestly an incredibly complex job. The PMIC has to be extremely efficient, because any energy wasted during this voltage conversion process is lost as heat, and, well, that just means shorter battery life. This is a huge focus for engineers. Even a small percentage improvement in PMIC efficiency can actually translate into a noticeable gain in how long your phone lasts on a single charge. It's not just about providing power, it's about providing it intelligently and without waste. And, the PMIC is also responsible for managing the battery charging process. When you plug in your phone, the PMIC is what communicates with the charger, determines the correct charging speed, monitors the battery's temperature and voltage, and makes sure it charges safely and efficiently. It's what enables fast charging standards and protects the battery from being overcharged, which is really critical for its long-term health and safety. It's basically the gatekeeper for all power entering and leaving the battery. So while the SoC gets all the glory for performance, the PMIC is arguably just as important for the overall user experience. A poorly designed power management system can lead to instability, overheating, and just terrible battery life, no matter how fast the processor is. On the motherboard, you'll often see the PMIC surrounded by a collection of tiny components called inductors and capacitors, which are all part of its power regulation circuitry. It's the quiet, diligent manager of the phone's entire power grid. A smartphone, honestly, isn't very smart if it can't connect to anything. The next set of crucial components we're adding to our motherboard are the wireless communication chips. This is a whole suite of radios that allow your phone to talk to the outside world. The most prominent of these is the cellular modem and its associated radio frequency, or RF, front end. The modem is the translator, converting digital data from the SoC into radio waves that can be sent to a cell tower, and vice versa. The modem itself is often integrated directly into the SoC, but the RF front end is a separate and complex system of chips, switches, and amplifiers. This system has to handle a huge range of cellular bands and frequencies, from the lower frequency 4G bands to the much higher frequency 5G bands, including millimeter wave. The placement of these chips and their antennas is really critical for getting a good signal. That's actually why you see those antenna lines on the metal frames of many phones. They're gaps that allow the radio waves to pass through. Next up, we've got the Wi-Fi and Bluetooth chip. Often, these two functions are combined into a single combo chip to save space. This chip handles your connection to your home or office Wi-Fi network for high-speed internet access, and it also manages all your Bluetooth connections to things like headphones, smartwatches, and speakers. Like the cellular radio, this chip needs its own antennas, which are also carefully routed within the phone's chassis to avoid interference. Another important, though less talked about, wireless chip is the one for NFC or near-field communication. This is the technology that enables tap-to-pay services like Apple Pay or Google Pay. It's a very short-range radio that allows for secure communication when your phone is just a few centimeters away from a payment terminal. The NFC antenna is often a large flat coil integrated into the back cover or even the battery of the phone, with contacts that press onto the motherboard. All of these wireless systems have to coexist in a really tiny space without interfering with each other. This is a major engineering challenge known as RF coexistence. The phone's software and the hardware on the motherboard have to be smart enough to manage all these radios operating at the same time. So, when you're on a phone call over VoLTE, streaming music via Bluetooth to your headphones and your smartwatch is synced in the background, it's this carefully orchestrated dance of wireless chips that makes it all seamless. So much of what we do on our phones involves sound. Whether it's making a call, listening to music, watching a video, or talking to a voice assistant, audio is just fundamental. But the digital ones and zeros inside the SoC can't directly drive a speaker, nor can a microphone produce a digital signal. There needs to be a translator in between, and that translator is the audio codec. Codec is short for coder-decoder. The audio codec is a specialized chip on the motherboard responsible for all things sound-related. Its primary job is to perform two-way conversion. It takes digital audio data from the SoC, like an MP3 file or the audio from a YouTube video, and converts it into an analog electrical signal that can be sent to the phone's speakers or the headphone jack if it has one. This is the decoder part of its job. It turns bits and bytes into sound waves you can actually hear. The other direction is just as important. When you speak into the phone's microphone during a call or while recording a voice note, The microphone picks up the analog sound waves and turns them into a weak analog electrical signal. The audio codec then takes this signal, amplifies it, and converts it into a digital format that the SoC can process and transmit. This is the coder or encoder part. It's constantly working in both directions. The quality of the audio codec has a significant impact on how good your phone sounds. A high-quality codec, paired with good amplifiers, will produce clearer, richer sound from the speakers and headphones. It will also result in cleaner, more intelligible recordings from the microphones. This chip is what handles features like noise cancellation for phone calls by using multiple microphones to identify and filter out background noise from your voice. On the motherboard, the audio codec is a small, unassuming chip, but it's connected to all the audio inputs and outputs. You'll see traces running from it to the connectors for the earpiece speaker, the main loudspeaker, the microphones, there are usually at least 2 or 3, and the USB-C port, which can also output digital audio. It's the central hub for the phone's entire audio system, making sure everything you hear and everything you say is processed correctly. Now let's talk about 2 components that are all about identity and expansion. These are the slots for the SIM card, and on some phones, the microSD card. While they might seem like simple mechanical parts, their integration onto the motherboard is essential for the phone's core functionality and user convenience. Let's start with the SIM card slot, which is the gateway to your cellular identity. The SIM card, which stands for Subscriber Identity Module, is what connects your physical phone to your account with your cellular carrier. It contains a unique identifier that tells the network, "This is me, this is my phone number, and this is my data plan." The SIM card slot on the motherboard is basically a reader. It has a set of spring-loaded pins that make electrical contact with the gold pads on the SIM card when you insert it. These connections allow the cellular modem to read the information from the SIM and register your phone on the network. In recent years, we've seen a shift towards eSIM, or embedded SIM. An eSIM is a tiny programmable chip that is soldered directly onto the motherboard itself. Instead of physically swapping plastic cards, your carrier information is downloaded and written to this chip digitally. This saves physical space inside the phone, which is always a plus for engineers, and removes a physical point of entry for dust and water. Many modern phones include both a physical SIM slot and an eSIM for dual SIM functionality. Then there's the microSD card slot. For a long time this was a staple feature, especially on Android phones. It's your phone's expandable attic. While the internal flash storage is your main filing cabinet, the microSD card slot allows you to easily and cheaply add more storage for things like photos, videos, and music. Like the SIM slot, it's a mechanical reader with pins that connect to the card, allowing the SoC to read and write data to it. However, the microSD card slot has become a bit of a rarity on high-end flagship phones. There are a few reasons for this. One is that external storage is significantly slower than the fast internal UFS storage, which can lead to a less consistent user experience. Another is that, like the headphone jack, it's a component that takes up valuable internal space and creates another opening in the phone's body. Still, for many users, the flexibility of expandable storage is a highly valued feature, and its reader is a key part of the motherboard's I/O capabilities. Modern smartphones are acutely aware of their surroundings. They know which way you're holding them, whether they're up to your ear, how fast they're moving, and where they are in the world. This awareness comes from a suite of tiny, low-power sensors that are constantly feeding information to the SoC. These sensors are soldered directly onto the motherboard, and they give the phone its sixth sense. First up is the accelerometer. This sensor measures acceleration, or the rate of change of velocity. Its most common use is to detect the orientation of the phone. When you rotate your phone from portrait to landscape to watch a video, it's the accelerometer that tells the software to switch the screen orientation. It's also used in fitness apps to count your steps by detecting the rhythmic motion of walking. Working hand in hand with the accelerometer is the gyroscope. While the accelerometer measures linear motion, the gyroscope measures angular velocity, or rotation. It provides much more precise information about how the phone is being tilted and turned. This is absolutely critical for things like 360-degree videos, virtual reality applications, and for advanced optical image stabilization in the camera, where it detects tiny handshakes and instructs the camera lens to move to compensate. Then there's the proximity sensor. This is usually located at the top of the phone near the earpiece. It typically uses an infrared LED to detect when an object is close to the screen. Its main job is to turn off the display and disable touch input when you hold the phone up to your face during a call. This prevents your cheek from accidentally hanging up or muting the call. A simple function, but a super important one for usability. And the list goes on. There's the ambient light sensor, which measures the brightness of your surroundings and allows the phone to automatically adjust the screen brightness. There's the magnetometer, which acts as a digital compass, telling apps like Google Maps which direction you're facing. All of these tiny sensors feed a constant stream of data to a low-power part of the SoC called a sensor hub, which processes the information efficiently without draining the battery. They are the invisible inputs that make so many smart features possible. Our motherboard is almost fully populated with chips and sensors, but it's still an isolated island. It needs to connect to all the other parts of the phone, the display, the battery, the cameras, and to the outside world. This is done through a variety of physical connectors and ports that are soldered onto the board. These are the crucial plug-in points that bring the whole device to life. The most prominent of these are the internal FPC, or flexible printed circuit connectors. These are tiny, delicate, zero insertion force connectors. You'll see several of them on the board, designated for specific components. There's a large one for the main display, another for the battery, and separate ones for the front and rear camera modules. These connectors allow for modularity. Components can be connected and disconnected, which is essential for both manufacturing and repair. Then there's the main external port, which on virtually all modern phones is a USB-C port. This single port is a marvel of versatility. It's soldered onto the motherboard, or sometimes a small daughter board connected by a flex cable, and serves multiple functions. It's used for charging the battery, for transferring data to and from a computer, and on many phones, it's also the primary port for audio output, replacing the old 3.5mm headphone jack. The robustness of this physical connection is critical. Beyond the main components, there are also connectors for smaller, but still vital parts of the phone. There will be contacts or a small connector for the vibration motor, which provides haptic feedback. There will be connectors for the earpiece speaker and the main loudspeaker, and there will be pogo pin connectors for the side buttons, the power and volume keys, which are typically mounted on a separate small flex cable that runs along the inside of the phone's frame. Each of these connectors is a potential point of failure, so their design and placement are carefully considered. They need to be secure enough to withstand drops in daily use, but also allow for efficient assembly in the factory. When you look at a fully assembled motherboard, you'll see it's a hub with ribbon cables branching out in all directions, connecting the central brain to all the limbs and sensory organs of the device. It's the final step in linking all the phone's hardware together. We have all our components placed. The SoC, the memory, the power management, the radios, the sensors, and all the connectors are on the PCB. But how do they get permanently attached? This is done through a process called soldering. For the vast majority of these tiny components, a technique called reflow soldering is used. First, a machine applies a solder paste, a mixture of tiny solder balls and flux, to the contact pads on the PCB. Then, another machine, called a pick-and-place machine, uses robotic precision to place each component onto the board in its designated spot, held in place by the sticky solder paste. Once the board is fully populated, it's sent through a long reflow oven. The oven has multiple zones that heat the board up according to a very specific temperature profile. This melts the solder paste, which then flows and creates a strong, permanent electrical and mechanical bond between every component and the PCB. After the main components are soldered, the board isn't finished. It often undergoes a cleaning process to remove any leftover flux residue. Then, larger components like the main ports or some shielding cans might be soldered on manually or using a different soldering technique. These metal shielding cans are placed over sensitive areas like the RF section and the SoC to prevent electromagnetic interference between components and to improve heat dissipation. Now comes one of the most critical stages: quality control and testing. You can't just assume everything worked. The assembled motherboard goes through a rigorous series of automated tests. A bed of nails tester might press down on various test points on the board to check for electrical continuity and make sure there are no short circuits. Then, the board is powered up, and specialized software runs diagnostics on every single component to ensure it's functioning correctly. Any board that fails a test is flagged and sent for analysis and potential rework. Only the boards that pass 100% of these tests move on to the final phone assembly line. This relentless focus on testing and quality control is what ensures that the phone you buy is reliable and works exactly as it's supposed to, day in and day out. It's the final crucial step in creating the heart of your smartphone. And that's how a smartphone motherboard comes together piece by piece. We started with a blank, multi-layered PCB and methodically built it up, from the powerful SoC brain to the memory and storage, the power grid, the wireless radios, and all the sensors and connectors that make a modern smartphone so capable. It's an incredible symphony of engineering, miniaturization, and precision manufacturing. The next time you pick up your phone, hopefully you'll have a new appreciation for the sheer complexity packed inside that slim device. It's a journey from a bare circuit board to the fully tested, intelligent heart of the machine. From the design of the copper traces to the final quality control checks, every step is critical. The level of integration required to make all these disparate components work together seamlessly in such a tight, power-constrained environment is truly one of the great engineering achievements of our time. And it's a process that continues to evolve with every new generation of devices. But what do you guys think? Was there a component or a process that you found particularly interesting? Or maybe you have questions about something we covered, or ideas for other tech breakdowns you'd like to see on the channel? Let me know down in the comments below. I read as many as I can. As always, thanks for watching. And if you enjoyed this deep dive, definitely consider subscribing to see more.